We have learned already how to identify if a bond is polar. In other words, if the electrons that make up the bond, the shared pair, is equally or unequally shared between the two atoms on either side of the bond. We also have learned how to predict the shapes of molecules. So one of the things we're going to do in this video is put together those two ideas and look at the overall polarity of a molecule. For a molecule to be polar, one thing that has to be true is it has to contain at least one polar bond. So I'm using the word molecular dipoles here. Molecular dipole means that the molecule has a polarity. So we could say the molecule has a dipole, or we could say it is a polar molecule. Those are both statements that mean basically the same thing. But another thing that has to be true for a molecule to be polar is that the bond dipoles, the polarity of the individual bonds, have to be in a structure in such a way that they don't cancel each other out. Let's take a look at three different cases. The easiest case is when there just are no bonds that are polar. For example, CH4. The only bonds in CH4 are carbon-hydrogen bonds. The electronegativity difference is so small that we consider that to be a nonpolar bond. So it does not really matter what the shape is, that will not be polar. The same thing is true for C2H4. It's going to have a different shape, but because the only bonds in here are either a carbon-carbon or carbon-hydrogen bond, this molecule cannot be polar. So as to the molecular polarity here, we could say that these would never be polar because they only contain carbon-carbon and carbon-hydrogen bonds. A slightly harder case is when we have polar bonds and they're all identical. We're going to have to look at a bunch of different instances to make a kind of a pattern here. We have to look at the shape of the molecule. That's one thing that we have to consider. And then try to make a determination about if the dipoles are going to cancel or not. If the bonds cancel out, then there's not going to be a molecular dipole. But if the bonds don't cancel, then the molecule is polar. So we'll look at a bunch of cases individually, and then we'll come up with a general rule at the end. So the first molecule we'll consider is a linear molecule. And when I say molecule, I just mean covalently bonded species. This could also be true for polyatomic ions, for ions that are covalently bonded together. As we go through these models, we're going to assume that all these bonds are polar and that the gray atoms are the ones that are the most electronegative. So as we lay dipoles on this linear molecule, we can see that the dipoles are in opposite directions, and because these are all identical bonds, those polarities are going to cancel out. We have unequal sharing between purple and gray, but overall on the molecule, these dipoles are going to cancel each other out. And so the result will be that this is not a molecular dipole. The next one is trigonal planar. Again, considering that the gray is the more electronegative to the two, and that this is all identical bonds, these are going to cancel each other out as well. You could do some trigonometry and actually calculate this out with the angles that are given, but in this kind of symmetrical molecule, what happens is the upward part of this bond balances the two downward parts of these two bonds, and the outward part of this bond here balances the outward part of that bond there, and everything cancels out in this symmetrical situation. So the result is that the bonds cancel and there's no molecular dipole. Next, let's consider a tetrahedral molecule. When we put the dipoles on there, this one's the hardest one to figure out. And once again, you could do a lot of complicated geometry, but it'd be three-dimensional. And the end result is that the downward component of each of these bonds here are about a third of a unit. And if this is the same polarity, that's 1. And so the downward 3 1/3 balances the upward 1. And so the ups and downs in this axis, they're balanced. And then in the horizontal axis, it's basically a trigonal planar for those components. So that cancels as well. So because this is symmetrical all around, the bonds cancel and there's no molecular dipole in the end. Trigonal bipyramidal. You can almost treat this as two separate molecules. There's a trigonal planar, which we've already seen shows bond dipoles canceling, and a linear. And we've already seen that shows that bond dipoles are going to cancel as well. So everything's canceled out here, and this is no molecular dipole for this species. Let's look at octahedral. Octahedral is like a linear and another linear and another linear. And so all the dipoles cancel, and so in the end, this is going to be a no molecular dipole. Now, we've only looked at the cases where there's no lone pairs on the central atom. So now let's look at the other shapes that are influenced by lone pairs. Here's a bent, and this could refer to either a bent 120 or a bent 105. If we put the dipoles on here, we can see that there's a downward component to each of these, but there is no upward component. There's a right and a left component that are going to cancel each other out, but those downward components are unmatched by any upward component, and so this is going to have an overall molecular dipole in the downward direction. So the gray end of this molecule is going to have more negative charge on average than the purple end of this molecule. And you can see that there's an overall big dipole drawn on this molecule. That's the direction of the negative charge. A trigonal pyramidal was another case where we had tetrahedral geometry, but one lone pair. If we impose our bond dipoles on here, again, we have three like 1/3 size downward dipoles, and in the horizontal plane, they cancel each other out, but there is no upward dipole to balance those downward components. And so overall, this is going to result in a molecular dipole because the bonds don't cancel each other out. Next, we have trigonal bipyramidal with one lone pair. That's a seesaw molecule. Put in our dipoles. Once again, we can separate this into two different situations. The axials are like a linear. They cancel each other out. But the equatorial bonds that are still there, well, that's just like a bent molecule. They don't cancel each other out. And so we're going to end up with an overall molecular dipole towards the downward part of the fulcrum, if you will, on the seesaw. T-shaped. This is a trigonal bipyramidal electron structure with two lone pairs. This is like a linear. That cancels out across the top of the T, but the vertical component of the T has nothing to cancel that dipole. So there's an overall molecular dipole downwards on the vertical member of this T-shaped molecule. Let's look at a square pyramidal. In a square pyramidal, when you put the dipoles on here, it's like a linear. Those cancel. And another linear. They cancel. But then there's another dipole that does not have anything to cancel it. So overall, the molecule is polar, and the molecular dipole points up to that top gray atom. One more, square planar. So this is an octahedral with two lone pairs. This is like a linear and another linear. And we've seen that they cancel each other out. So in this case, the bonds cancel, and there ends up being no molecular dipole. Okay, so let's summarize this. We can make a conclusion that if all bonds are to the same element, a symmetrical molecule is always going to show nonpolarity. So all the examples, linear, trigonal planar, tetrahedral, trigonal bipyramidal, octahedral, and square planar that were symmetrical, they ended up being nonpolar. But all the asymmetrical ones ended up being polar. So that's the bents, trigonal pyramidal, seesaw, T-shape, square pyramidal. All of those are asymmetrical, and they all ended up being polar. Now that's only if all of the bonds to the outside atoms are the same. Let's look at some examples. CO2. When we draw the Lewis structure for CO2, we're going to skip over the steps here. You should do them if you're still not familiar with this. This is a linear molecule. CO is a polar bond. The oxygen is more electronegative than the carbon, but because it's linear, they cancel each other out, so this is nonpolar. Let's look at another one. H2O. When we draw the Lewis structure, done this before, this is what we get. Because the steric number is 4 and there's two lone pairs, that means this is a bent molecule. An OH bond is definitely polar, with the oxygen end being the more electronegative end. So these things do not cancel, and we have an overall molecular dipole towards the oxygen end. So that means the hydrogen side is a little bit positive, and the oxygen side is a little bit negative. NH3. When we draw this Lewis structure, this is how it ends up. Steric number 4, 1 lone pair. That means it's trigonal pyramidal. So to draw this out, something like this. Nitrogen is more electronegative than hydrogen. So these dipoles are all facing towards the nitrogen. And this is asymmetrical molecule, so the bond dipoles do not cancel, and we end up with an overall molecular dipole towards the nitrogen end. NO2 1 minus. When we do the Lewis structure, this ends up with a double bond and a single bond, which means that it's probably resonance going on here. Steric number is 3. There is 1 lone pair, so this is a bent molecule. Oxygen is more electronegative than nitrogen. So these don't cancel because it's asymmetrical, and we end up with an overall bond dipole with the oxygen end being the more negative end. SF4. Lewis structure ends up looking like this. The fluorines are on the outside. They have full octets. Not so important for our analysis, but we needed to have more electrons than this because sulfur gives us 6, fluorine gives us 28, so this should have 34 electrons. And we have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. Sulfur needs another lone pair. This is steric number 5 with 1 lone pair, so this is a seesaw molecule. So when we think about drawing this, we have our sulfur in the center. It's going to be an axial fluorine up here and axial fluorine down there. And then there'll be a fluorine here and a fluorine here. These two dipoles, fluorine's more electronegative than anything, so those are definitely dipoles. Those two cancel. But the dipoles facing out towards these equatorial fluorines, there's nothing to cancel those, so there's an overall molecular dipole towards the fluorine side of that asymmetrical tetrahedron in the seesaw. Here's another example, PCl5, Lewis structure look like this. And I'm not going to put the lone pairs on the chlorines because for our purposes we only really need to know the shape, and that's not influenced by anything in the outside atoms. So this ends up being a trigonal bipyramidal molecule because it's steric number 4 and there are no lone pairs in the central phosphorus. And that's a symmetrical. And so the bond dipoles are all going to cancel. We can sketch it out. Chlorines are here, here, and here. Phosphorus in the center. There's a chlorine up here and a chlorine down here. Chlorines are more electronegative than phosphorus, so there's a dipole facing out towards all these chlorines, but they cancel, just like a trigonal planar would. And the up and down on the axial, those cancel as well, just like a linear would. So overall, this is not a polar molecule. ClF3. When you do this Lewis structure, chlorine goes in the middle, fluorines go on the outside. There's 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. But this should have 4 times 7, which is 28 electrons. So we need another pair. So this is steric number 5, 2 lone pairs. That means it's a T-shaped. So literally the way this Lewis structure is drawn is the shape of the molecule. Chlorine and fluorine. Dipole is going to go towards fluorine. Dipole towards fluorine there. Dipole towards fluorine there. The ones that go left and right in this drawing, they're going to cancel each other out, but nothing cancels out the one that goes straight up. So our overall molecular dipole is towards that upper fluorine. Xenon tetrafluoride. When we do this Lewis structure, it ends up looking like this. And xenon gives us 8, fluorine gives us 4 times 7, which is 28. So this should have 36 electrons in it. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32 with the bonds, 34, 36 with 2 extra lone pairs on the central xenon. This is steric number 6 with 2 lone pairs. This is a square planar, so it's literally shaped just like what we have drawn. Fluorine is going to be more electronegative than anything. So we have a linear that way and another linear that way. They cancel each other out. This whole molecule is going to be nonpolar. Here's another one, BRF5. This is 6 halogens basically, so that's 42 electrons, 6 times 7. Put the bromine in the center. Put 5 fluorines. I think I put too many sticks there. 5 fluorines on the outside. And fill octets. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, and then with the bonds, 32, 34, 36, 38, 40. We need another lone pair. So this is going to have steric number 6, 1 lone pair. This is a square pyramidal. Square pyramidals are asymmetrical, and so this should be polar. We'll sketch it out. Central bromine is here. We have a fluorine, 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 fluorine here. The dipoles are going to face towards fluorine like they always do because fluorine is the most electronegative thing there is. And then we got this upper fluorine, but there's no downward fluorine because there's just a lone pair down here. So these dipoles cancel, but this one has nothing to cancel it out, so that's the overall molecular dipole. It's a polar molecule. One last one, SF6. When you drew the Lewis structure for this, this is what you end up with. There are no lone pairs in the central atom. I'm not going to fill in the octets on all the fluorines. This is octahedral, no lone pairs. So that means it's an octahedral molecule, and octahedrals are symmetrical, and so all the bonds are going to cancel. Just to sketch it out, there's a fluorine on each corner, sulfur in the middle, fluorine up here, fluorine down here. This dipole cancels this dipole. This dipole cancels that dipole. And this dipole cancels that dipole. So the whole thing is nonpolar. The much harder case is when the bonds are not all too identical outside atoms. So here you have to consider 2 things. One is the shape of the molecule, but the other thing you have to look at is the individual bond polarities. This isn't going to arise too much in this class, but let's consider a couple of examples. Here's CH3Cl. If we're going to draw the Lewis structure for this, it's going to have to end up having 4 electrons plus 3 plus 7. So that's 14 electrons total. Because carbon's closer to the middle of the periodic table, we'll put it to the middle of the structure. Hydrogens have to be on the outside, and halogens usually make 1 bond, so we're going to put chlorine on the outside. That makes sense. Let's fill the octet on chlorine. Carbon's octet's already full. And then do our count. So that's 1, 2, 3, 4, 5, 6, 8, 10, 12, 14. The structure is correct. Okay, carbon-hydrogen bonds are not polar at all. A carbon-chlorine bond is polar. Chlorine is more electronegative than carbon, and so we do have a dipole there. What's the shape of this thing? Well, it's going to be tetrahedral because it's steric number 4. I'm going to draw it this way. Put the chlorine on the top, hydrogen down here, another hydrogen out towards me, and that 4th hydrogen kind of back in the other way. Okay, so there is a dipole here. It's canceled by nothing, so there's an overall molecular dipole towards the chlorine. Okay, HBF2. We're going to draw the Lewis structure. That's going to be 1 electron plus 3 for the boron plus 2 fluorines give us 14 electrons. So that's an overall 18 electrons in our structure. We'll put boron in the middle. We're going to attach an H to it, and then we're going to attach 2 Fs to it. Fill octets, 2, 4, 6, 8, 10, 12. Boron does not get a full octet because 6 electrons is stabilizing for boron. If we do our electron count, we have 2 fluorines with 6 electrons in lone pairs each. So that's 12. And then 14, 16, 18 with the bonds. That's the right structure. What's the shape? Well, this is steric number 3. No lone pairs, so it's a trigonal planar. The BF bond is polar. There are 2 of them. They do not cancel each other out, and so we end up having an overall molecular dipole kind of in this direction. All the molecules that we've been looking at have a single center, but the thinking still applies for multi-centered molecules. Here, this one is ethanol. It's an alcohol. It's the alcohol that's in alcoholic beverages. When you end up drawing the shape for this thing, I'll just skip a few steps here. This is what it looks like. There's going to be a hydrogen attached there, and there, and there. Another hydrogen attached here and here. And carbon-hydrogen bonds are not polar, so nothing over here is polar. Nothing in the middle is polar, regardless of shape. These are all tetrahedral, but it doesn't really matter. This does represent some polarity. Oxygen is more electronegative than carbon, so there's a dipole there. And it's also more electronegative than hydrogen, so there's a dipole there. And this is a bent molecule. That section of this molecule is asymmetrical, so there is an overall dipole towards the oxygen end of this piece of the bond. So part of this molecule is not polar, but part of it is polar. Here's another example. This is acetic acid. This is the acid that's in vinegar. When you draw this out, this is what this structure is going to end up looking like. And once again, we have one end that's nonpolar because there's no bonds that are polar in there. But a carbon-oxygen bond, that's polar. This carbon-oxygen bond, also polar. This hydrogen-oxygen bond, also polar. So there is no electronegativity being canceled out. And that means this is going to be a polar molecule. Kind of in this direction, I guess, because this dipole is 120 degrees from these other 2 dipoles. But it is going to end up being polar. So these last 2 examples give us a little bit of a clue as to a shortcut. One of the things that is going to be very common is that you will see polarity in molecules that contain an OH bond.